We can continue with curve sketching. Now I'm going to do the second example in your handout. F of x equals x squared minus 4 over x cubed. Again, we are going to follow the same steps. Start with the x-intercepts. To get the x-intercepts, you need to factor f of x. So numerator is x minus 2, x plus 2, and denominator is x cubed. So based on that, we take the zeros of the numerator. We get 2 and 0 and negative 2 and 0. Now let's get y-intercept. Substitute 0 in f of x. If we do that, we see that f of x becomes undefined. We can't have 0 for denominator. Therefore, there is no y-intercept. Now let's look at the asymptotes. So whatever makes denominator 0 gives you the vertical asymptotes, or zeros of the denominator gives you the vertical asymptotes. In this case, x equals 0. So vertical asymptote, x equals 0. Let's look at the horizontal asymptote. Degree of numerator is less than the degree of denominator. So that gives you horizontal asymptote at y equals 0. Next step is getting local max and min points. So let's take the first derivative of the function. Let's remember, if you have a rational function, when you are taking the derivative, you need to apply the quotient rule. So derivative of the numerator, 2x, times denominator, minus derivative of denominator times the numerator, over square of the denominator, x to the power of 6. Now we need to simplify this. So I have 2x to the power of 4 minus 3x squared times x squared minus 4 over x to the power of 6. Now we see that x squared is a common factor between those two terms. So x squared, I'm going to take that out. So we have 2x squared minus 3x squared minus 4. Let's simplify x squared and x to the power of 6. That gives us x to the power of 4 for denominator. And now expand this. 2x squared minus 3x squared gives you negative x squared. Negative 3 times negative 4 gives you positive 12. I'm just going to factor negative sign from numerator. That will help me to find the zeros of the first derivative. So when we are doing the first derivative test, again we are going to take the zeros of the first derivative. So make numerator 0. So you get x squared minus 12 equals 0. So you get x squared equals 12. X is plus and minus square root of 12. So that gives you plus and minus 2 root 3. So we are going to have negative 2 root 3 and positive 2 root 3. But we also need to include our table where the first derivative is undefined. In this case, when x is 0, first derivative is undefined. So we need to add that value in our table. Now we are going to check the sign of the first derivative. So it would be helpful if you just also calculate the decimal value of those radicals. So we get negative 3.5 here and positive 3.5. So pick a value that is less than negative 3.5. Let's say negative 4. So in here, negative 4 squared is 16. So this is positive times the negative value is negative. This is always positive, so not affecting the sign of the first derivative. So we only get the sign of the first derivative only from the numerator. Okay, so we get negative value here. And then apply the same thing, pick a value here and calculate the sign of the first derivative. then f is decreasing from negative infinity to negative 2 root 3, increasing here, increasing and decreasing. Now check where the sign of the first derivative changes. So it looks like at negative 2 root 3. So therefore we are going to have a local minimum here because it's changing from decreasing to increasing. Okay, and also here it is changing from increasing to decreasing at 2 root 3, and we have a local maximum points there. Now we need to calculate the y coordinates of those points. So I'm going to take negative 2 root 3 sub in the original function. Okay, so we get negative 2 root 3 square minus 4 over negative 2 root 3 cube. So this gives you 4 times 3, 12, minus 4 over negative 2 cube is negative 8, root 3 cube is 3 root 3. So we have 8 over negative 24 root 3. So that gives you negative 1 over 3 root 3. Rationalize the denominator. You get negative root 3 over 9. Negative root 3 over 9. And if you do the same thing for the other point, you get positive root 3 over 9 here. If we write increasing and decreasing intervals, increasing from negative 2 root 3 to 0, and from 0 to 2 root 3. Again, you may be wondering why we are not taking 0 here, and remember that makes first derivative also the original undefined, so we should not be including 0 here. Decreasing intervals from negative infinity to negative 2 root 3, and from 2 root 3 to positive infinity. Now let's go check the second derivative. I'm going to use, of course, the first derivative here, and then take the derivative of the first derivative. Okay, derivative of numerator, negative 2x times the denominator, x to the power of 4, minus derivative of denominator, 4x cubed, times the numerator, negative x squared plus 12, over square of the denominator, we get x to the power of 8. Now we need to simplify this. Negative 2x to the power of 5. I'm going to keep this for now because I want to factor. So common factor is negative 2x cubed. So we get x squared here plus 2 times negative x squared plus 12 over x to the power of 8. Simplify the denominator with this x cubed, so you get x to the power of 5, negative 2, expand this, x squared minus 2x squared gives you negative x squared plus 24. So I'm going to factor negative 1 from here, from this bracket. So we end up with 2 times x squared minus 24 over x to the power of 5. Again, to do the second derivative test, I need the zeros of the second derivative and whatever makes second derivative undefined. In this case, so let me take this factor, make it equal to 0. So we solve for x. So we get x equals plus and minus square root of 24. Simplify it, plus and minus 2 root 6. So let's create the second derivative table. So we're going to use negative 2 root 6, positive 2 root 6, and 0 makes second derivative undefined. So I have to take that value here as well. Now let's check the sign of the second derivative. So to be able to do that, first convert those radicals into a decimal value. That will help you. This is negative 4.9 and this is positive 4.9. So pick a value that is less than negative 4.9. So let's say negative 5. Sub in here 25, 24, positive. That is negative. So you get a negative value here. Pick a value between negative 4.9 and 0. Sub in again in the second derivative to calculate. So you should end up with these signs. Then f is concave down here, concave up, concave down, concave up. So let's check the point of inflection. Function is changing from concave down to up at negative 2 root 6. So we have 1 point of inflection here. Original function is changing from concave up to down at 0. However, 0 is not point of inflection because that is the vertical asymptote, and 0 makes original function and the second derivative undefined. So that is not the point of inflection but vertical asymptote. Okay, and here 2 root 6. So function is changing from concave down to up. So we have another point of inflection. So let's calculate the y coordinates of those points. Okay, so I'm going to substitute 2 root 6 in the original function. And also negative 2 root 6. If you do that, you get negative 5 root 6 over 72, or as a decimal value, you get, oh, that's positive, okay, so positive 0.17, okay, and if you substitute negative 2 root 6, you get negative 5 root 6 over 72, or negative 0.17. So those are my inflection points. So I'm going to put here negative 5 root 6 over 72 and positive 5 root 6 over 72. And as a decimal value, because I need those decimal values to put it on my graph. So negative 4.9, negative 0.17, positive 4.9, and positive 0.17. We could also write the concavity, intervals for concavity. So let's do that. Concave up. Then we have from negative 2 root 6 to 0, and from positive 2 root 6 to positive infinity. Concave down, negative infinity to negative 2 root 6, and 0 to 2 root 6. Let's sketch the graph. So let's put our x-intercepts. We have 2 and 0, negative 2 and 0. And y-intercept, we don't have any. Now let's put vertical and horizontal asymptotes. X equals 0. y equals 0. You also need to put local max and min points. So we have one at negative 3.5 and negative 0.19. Negative 3.5, negative 0.19. And we have another one at 3.5 and negative, we have at 3.5 and positive 0.19. Okay, what else we have? Point of inflections. We have those at negative 4.9 and negative 0.17. Another one at 4.9 and positive 0.17. Now we need to actually analyze, put those tables, two tables together to analyze the shape of the curve. Let's do that. To be able to do that, again, we need to take all the values from first derivative table. So we have negative 2 root 3. We said that is negative 3.5. We have 0, positive 3.5. From the second derivative table, we have negative 4.9, 0, positive 4.9. Put them in order. So we have negative 4.9, negative 3.5, 0, positive 3.5, and positive 4.9. Okay, so now I'm going to apply the information from the first derivative table. F is decreasing from negative infinity to negative 3.5. So decrease here. Increase between negative 3.5 and 0. Increase between 0 and positive 3.5, and decreasing when x is greater than 3.5. So let's check the second derivative table. When x is less than negative 4.9, it is concave down. When x is between negative 4.9 and 0, concave up. Concave down between 0 and 4.9. And then it is concave up when x is greater than 4.9. Again, we are going to use the face to come up with the shape of the curve. First interval, decrease concave down, decrease concave down, decrease concave up, decrease concave up, increase concave up, increase concave down, decrease concave down, and decrease concave up. Okay, now let's apply this table, this information into our graph. We said that, okay, so when x is between negative infinity to negative 4.9, it is going to look like this. Make sure to approach to the asymptote. Between negative 4.9 and negative 3.5, it should look like this. Between negative 3.5 and 0, should look like this. And make sure to pass through the x-intercept and approach to the vertical asymptote. Between 0 and 3.5, this is the shape. And make sure you pass through again the x-intercept. between 3.5 and 4.9 should look like this. And then when x is greater than 4.9, it should look like this. Make sure again to approach to that horizontal asymptote. Okay, so that is a solution for example 2.